Hypothalamus Artificial Intelligence, HI. Digital transformation powered by autonomous and intelligent algorithms in real time. Presents its solutions based on artificial intelligence for decision-making for high-power, natural gas field exploitation planning using optimization Bi-Sectorial model. HI has the support of its technological allies, General Algebraic Modeling System, GAMS, and IBM, producer of C-PLEX Optimization Studio. Both products are incorporated into HI's artificial intelligence solutions. The first version of high power, called SHTG, Hydrothermal and Gas Dispatch System, was awarded the Colombian Engineering Award by the Colombian College of Engineers, SEAM, in 1998. SHTG was developed for a global oil company, to jointly analyze the electricity and gas markets. The oil company kindly authorized HI, then Decisionware, to submit the work, withholding the name and maintaining all confidentiality of the data and results. SHTG was implemented using OptEx, the optimization expert system. Presence. Use case, Oil Express natural gas field exploitation planning. At the end of the last decade of the last century, Oil Express, a global natural gas company, that operated several natural gas producing fields in multiple countries, asked HI for support to define a natural gas field exploitation planning strategy, using highly complex mathematical models, to analyze the entire decision-making environment. The challenge was to develop a model that supported the decision-making, regarding the exploitation of natural gas field, and its impact on Oil Express finances. Solution: design and implementation of a DSS for management of natural gas oil field strategic decisions like the exploitation period. The models included in the DSS were electricity and gas economic dispatch simulation, optimization of the gas trading decisions, optimization of the financial and fiscal decisions, and financial simulation of the gas buyers. Result: the SHTG model, hydrothermal and gas system, the first version of the actual high-power model. Based on the high power, Oil Express makes its decisions that produced successful results that led to higher profits by delaying the exploitation of the gas field for an economically more convenient time, due to the non-sustainability of the market. High power integrates the following models. High electricity supply chain optimization supports decisions in the electricity supply chain, in terms of sectoral planning and business generation. High smart grids optimization supports the decisions of the various agents involved in the smart grids business. High natural gas supply chain optimization supports the decisions of the actors involved natural gas supply chain, at the level of sectoral planning and business generation. The following is the topology of high power. Hydraulic system physical modeling. High water corresponds to a general model that includes all kinds of hydraulic components, reservoirs, hydroelectric power plants, rivers, overflow channels, connection points and pumping stations, demands, like irrigation, aqueducts, environmental, industrial. Components can be freely linked to form any topology, like pumping storage systems. Hydroelectric power plants are modeled independently of reservoirs, so plant-reservoir connectivity must be established. The regulation capacity of the reservoir is simulated in detail, so such a simulation consistently represents the dispatch of the power plants, considering their ability to regulate the multi-annual, annual, hourly water resource. Electric system physical modeling. Electrical connectivity is carried out through a network of circuits and bars that integrates different types of installations, power plants, like hydroelectric, thermoelectric, coal, wind, solar, biomass, places of demand, like industrial, cities, regional interconnections and energy storages. High power includes the simulation and several types of renewable energy sources and energy storages. For each type of electrical asset, high power includes the exact equations for simulation. Natural gas system physical modeling. High gas describes the process of supply and demand of natural gas. From this point of view, its integration with the electricity system determines the economic equilibrium electricity-gas markets. The entities of the natural gas system are node, connect the gas system installations, production fields, consumption zones, discriminated by sector, example, refineries, heavy industries, residential, vehicular, and commercial thermoelectric power plants. Transport systems, I, pipelines and 2, multimodal transport systems using vehicles, pumping stations, compress the gas to transport it, and ports, receive and ship liquefied natural gas, LNG, and have gas storage capacity. Connectivity between the electricity and gas sectors occurs through the demand for natural gas for use in thermal plants, and the substitution of the demand that can occur between gas and electricity. Analysis of the gas market for the electricity sector. The main study carried out with high power was the analysis of the national gas market for the electricity sector. This is due to no alternative markets for natural gas other than national electricity generation. Pressure from the electricity regulator to sign contracts by generators and producers of natural gas for the purchase and the transportation of natural gas to give firmness to the electricity sector. Oil Express fundamental hypothesis: if the gas market is not sustainable, it makes no sense to sign bilateral contracts with electricity generators and to invest in extracting the natural gas, and the optimal strategy is to wait for the right moment in the future. The analysis was carried out using take-or-pay contracts as a basis. The take-or-pay (TOP) is a contractual clause, requiring the buyer to take the delivery of a specific amount of goods or services from the seller or pay a fine if they do not. Thus, it protects the seller against potential losses if the buyer refuses to complete the purchase by a particular date. A top clause is common in energy industries, including oil, natural gas, mineral, and coal, seeking significant investment. It is also called the kill clause. The contract is normally signed before the companies start oil, natural gas, minerals, or coal exploration. Therefore, it is a type of offtake agreement. A top clause is common in energy industries, including oil, natural gas, mineral, and coal, seeking significant investment. It is also called the kill clause. The contract is normally signed before the companies start oil, natural gas, minerals, or coal exploration. Therefore, it is a type of offtake agreement. Given the seasonality of prices in the electricity sector, the model included top with a rolling period, which gives flexibility to the buyer to accommodate their physical purchases. But it complicates the generator decision-making process. To stimulate the natural gas market for the electricity sector, government institutions conducted a reference study. This study was taken as a reference to analyze the market using the SHTG model. The main characteristics of the study was: the rolling period was 6 months. 10 plants were considered for take-or-pay contracts with an installed capacity of 2,813 megawatts. The take-or-pay percentage was 30% for the plants of the center and 70% for the plants in the border, and the electricity dispatch planning model used by ISO operator was adapted to represent the impact of TOPS. The table presents the summary of the characteristics of the scenario studied by the regulator to stimulate the signing of contracts in the natural gas market. The percentages of TOPS fixed do not come from an optimization model, they were perceptions of what should be. The chain of qualitative effects, which derive from top contracts, is relatively easy to foresee. The bid price of the thermal plants to the spot market will go down. This is because they have turned the variable cost into a sunk cost. In the extreme, it could reach zero. This will lead to an increase in the dispatch capacity of thermal plants, and the fall in spot prices. As the volume of natural gas contracted through TOPS increases, it can be expected that hydro plants will lose share, thermal plants will gain participation, and the spot price go down. It is clear an economical resource, but not 100% reliable, hydroelectric energy, is being exchanged for another more expensive but more reliable, thermal energy. It should be considered as a risk premium. From the point of view of income, we have revenues from hydro generators will decrease, and the change in the income of thermal generators cannot be evaluated a priori. Therefore, a mathematical model is required to evaluate quantitatively the natural gas market. Modeling take-or-pay contracts. To carry out the study, 5 cases were implemented to consider the top modeling. The following is the code associated with the modeling and description. No top, no contracts. Libre, optimized contract generation. Equations are included in the dispatch model, high power, to accurately represent top contracts. Rodante, minimum rolling generation. The minimum generation of the thermal plant is forced during the rolling period, to ensure compliance with the contract. Mensual, minimum monthly generation. The minimum monthly generation of the thermal plant is forced, to ensure compliance with the contract. More restrictive than the previous one, and MWKTE, fixed generation at the base. The thermal plant is forced to generate in the base, permanently, to ensure compliance with the contract. More restrictive than the previous one. All forced generations can be implemented with an economical dispatch model, without requiring modifications to the model. All these imply losses for thermal plants, when the marginal costs of electricity are below the variable cost of top. Top contract modeling implies dividing the thermal generation in GT0 thermal generation with cost equal to variable OM costs excluding fuel cost. Typo 0, limited by top contract, and GT1 thermal generation with cost equal to variable OM costs plus fuel cost. Type 1, non-top contract. GT, the total thermal generation, must be equal to GT0 plus GT1. There is only one appropriate way to study top contracts, and in general any bilateral contract. Model the operations and the financial transactions as they are described in the contract. Approximations to this modeling will only bring economic losses for the generators and for the society. For example, trying to adapt an economic dispatch model, by parameterizing the dispatch of thermal plants, will bring negative consequences for all market agents. All forced generations can be implemented with an economical dispatch model, without requiring modifications to the model. But all these imply losses for thermal plants, when the marginal costs of electricity are below the variable cost of top. Scenario aggregate economic results. Following the logic, the most economical option is not to consider the top contracts. When including the top, a risk premium must be assumed, which could be established as the difference between optimized contract generation and no top contracts. In this case it implies 26% of cost overruns. The last three cases involve overcosts due to the poor quality of mathematical modeling. As poor quality increases, cost overruns increase. It must be interpreted that if we implement low quality models, this will translate into more expensive operations, which will pay someone in the market. The first candidate is the user of the models. It can be noted that the optimal allocation of energy take or pay is a function of the rolling period, and it is far from a constant allocation. Under economic rationality, thermal generation GT0 must be allocated in the blocks in which it substitutes more expensive energy, block BO3. When it is assumed that the thermal generator will not generate at a loss despite the take or pay, the thermal generation decreases to the economic optimum level for the generator, conditional on it already has a top. In the bad modeling cases, the generator is forced to an additional loss to that caused by an inadequate top amount. Taking marginal cost as a proxy for the spot price of electricity can be stated, it should be expected that the highest spot price will be for the market without top contracts. From this level, the spot price of the market will go down. The graph presents the nodal marginal costs. To quantify the financial impact of take or pay contracts, we can consider the estimated operating income for generators, defined as the marginal cost, a proxy of the spot price, multiplied by the generation. Since the spot price goes down due to the top, the highest value reference is the market with no contracts. In this case, for simplicity, the post-optimization financial impact has been evaluated, using the resulting dual variables as a reference. However, it should be noted that high power can solve an PEC, mathematical problem with equilibrium constraints, problem in order to convert the financial impact into part of the optimization model, and thus obtain a more accurate view of the health of the market. The effect for hydraulic generators, which generate less, and receive less remuneration for each MWH generated, the negative effect is evident. For thermal generators with top, the increase in generation, could be produced a higher operating income. The impact can be summarized as: top contracts as proposed adversely affect the aggregate of all generators, and when mathematical modeling practices are incipient, this will negatively affect the market. A good way to present the financial information is the accumulated curve of estimated operating income over the entire planning horizon. The graph shows operating income of hydraulic generators. These graphs presented the aggregation of all generators, but they exist for each individual generator. In the case of this hydro generator, paradoxically its financial health does not depend on its actions, but on that of other agents. If thermal generators assume a rational position, the financial health of the hydro generator will not be affected. But, if they assume an irrational position, ignoring mathematical laws, the hydro generator can go bankrupt. In simple terms, this defines an externality undesirable in a market, in which the errors of an agent can be paid by other agents. The golden rule is everyone pays for its own mistakes and takes advantage of their right decisions. The situation of thermal generators is different. For the planning period analyzed, the costs of top contracts cannot be recovered. The financial damage will be greater if the decision handling is not based on specialized mathematical management models. The graph indicates a general crisis of the thermal generators if the top indicated by the government are signed. The graph shows that the financial health of a specific thermal generator may depend on its management capacity, and that if there is an exit, the generator can become profitable in a market in difficulties. High power allows Oil Express to financially analyze all market participants, both potential customers and clients of the competitors, which allows Oil Express to perform the scientific market intelligence activities. Considering that the proposal of tops made by government entities does not come from an optimization process, but were defined considering logic and good practices, Hale and Oil Express proceeded to make an adjustment in the value of the tops, so that they approached an optimal value, and thus analyze the behavior of the market in these conditions. These adjusted values do not come from an optimization process. However, it should be noted that the high-power model can be used to determine optimal top values. The graph presents the comparison of the results for the cost recovery of hydraulic generators. Values set based on mental rules can affect the market, even bankrupting it. It could be concluded that the greatest damage that can be done to the market is to establish reference values without justified mathematical support. Since there are values of the tops that minimize the values of the risk premiums for reliability, without profoundly altering the economic behavior of the market. It is coherent that if the thermal generators act rationally, they do not drastically affect the hydraulic generators as a consequence of their bad decisions. In the case of cost recovery of thermal generators, the situation is more complicated, due including the optimal values for the tops will generate problems of bankruptcy and liquidity, which will be more serious if the top values do not have an appropriate rationality. This indicates that the electricity market cannot guarantee that thermal generators can pay the top contracts that are theoretically required by the government. Successful decisions. For its part, Oil Express has proven that there are no market conditions, that is, do not exist a good set profitable thermal generators that can pay for gas through TOPS contracts, required to guarantee the extraction of natural gas. If it is a question of compensating the situation based on price, if Oil Express sells natural gas at high prices, it is possible that Oil Express must recover bankrupt industrial company assets. Everything seems to indicate that the optimal decision may be to delay the investment, waiting for a market with better conditions. Use case: surveillance of the electricity and natural gas sector. A supervisor of the electricity and natural gas sectors hired High to solve the following problem. Challenge: to develop a decision support system, DSS, to surveillance activities for the electricity and natural gas sectors. Solution: design and implementation of the DSS that included the following models: electricity and gas dispatch, competitive electricity market equilibrium, real dispatch of the interconnected system considering the long-term contracts of purchase-sale of natural gas and electricity, and financial statements of the electricity generators considering the real dispatch. Result: a DSS that integrates the models required by the supervisor, based on high power. Like Herbert Simon, Hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.